Welcome to my channel AI Basics with AK. Here we are with another new episode with our season 3 introduction to statistics on episode 9, the T distribution. Let's recap what we have discussed in our episode 7, which is central limit theorem. If we have remembered, the intuition behind central limit theorem is that if we take independent samples from any distribution, it can be from uniform, it can be binomial, anything, then the distribution of sample means become approximately normal as the sample size increases. So that's what it is. Like for large sample sizes, the sampling distribution of sample mean is approximately normal. This is the core of CLT. Even though we don't remember the population standard deviation, even with sample standard deviation, we can construct what could be the population distribution for those sample means. Based on those sample means, we can construct what could be the population distribution. And as we have discussed in our next episode, that's the confidence intervals, like what could be the population mean based on the sample and how much confident we are. Now assume that, okay, sigma is of course unknown, but the sample size is very small, so our confidence drops. But assume that the sample size is further small, where we cannot apply the central limit theorem, which is a G statistics, like it does not tend to be a normal. In that cases, luckily, the statistics has given comfort with a T distribution. So in practice, sigma is rarely known, which is the fundamental factor, right? We don't know about the population. We always take the sample. If the sample size is very small, that's where the T distribution kicks in. How do you define whether it has a sufficient sample? It's usually, the thumb rule is usually, they take it as number of samples as 30. Where does this come from? Is usually the concept of something called a degrees of freedom. What is the degrees of freedom? It is a statistics that indicates the number of independent values that can vary in an analysis without breaking any constraints. So what does it put it simple means? Say for example, what is your freedom? Put it simple. What is your freedom when your sample size is only 1? Freedom is 0. So it means, are you confident ideally? No, because with one sample you cannot be much confident. As our freedom increases, okay, you will be more confident and the distribution changes. Maybe it turns to be a normal distribution. So this is called a degrees of freedom, which is usually used in computing our sample statistics and how much significant it is. Because if the degrees of freedom is less, what it is means it is more ambiguous and we cannot predict it. As we increase the degrees of freedom, it means there is a statistical significance that the distribution is much predictable and we are more confident about it. So think in that manner about conceptually what is a degrees of freedom. Now let's move to the next slide. So to put it simple, like assume the T distribution is also like a normal distribution for this slide. Okay, but however, when the degrees of freedom is very small, what it means, it has a heavier tails. It means my unpredictability is much more higher and I'm not confident whether the distribution will be thicker or uniform. So put it very simple, if there is a distribution which is very uniform and you want to predict a population mean, if it is very uniform, it can vary from 0 to 100, isn't it so? So to practically, we cannot guess the population mean because it can lie anywhere between 0 to 100. But As we increase the samples, okay, maybe it will change something like this. It will change something like this. So you will be much more confident what could be the population mean depending upon our problem at hand. So here you are not confident here, right? It can be anywhere between. Here at least, okay, we are getting confident. So the smaller the DF, the tails are much more heavier because you have larger uncertainty about what could be the population. Larger the DFs, okay, it becomes closer to the normal because you have reduced your uncertainty, because you have, you know, more about the world, because you collected large amount of samples, and statistics says that, okay, I know about this pattern, I'm confident, pretty confident about what could be the population mean. That's how statistics helps in terms of inferring what could be the population based on our statistics. Beautiful, isn't it so? Now, I have given you that visualization, but I'm just giving you an think before jumping into the next slide. You know about the standard normal distribution, and think how it look when the t distribution is with degrees of phi. I mean the degrees of freedom with phi, and also a t distribution with degrees of freedom is equal to 20. Just the heaviest tail, of course, okay, will be at degrees of freedom, which is equal to phi. As we increase the degrees of freedom, as we have discussed before, what will happen? It tends to become normal. Beautiful, right? At what point do you think it becomes undistinguished about normal? Usually the people say which is degrees of freedom ideally greater than 30, but always we can always check with respect to the sample data we have it, because at times most of the universal samples data this might be applicable, but there are some cases where maybe we might be requiring more larger data because of the uncertainty about the real world problems. Got it? Now this is a simple distribution, as you can see here, okay. The blue is a degrees of freedom is equal to 5. You can see the heavier tail. It means the confidence is not so great because there is a higher probability that it could fall anywhere here, like it is occupying this probability space as well. But as you increase the sample size, which is nothing but your degrees of freedom is increasing, it tends to become little bit normal, 20, and maybe at 30 here it becomes more normal. So this is just a random number generator. Even if it is a random number generator, you can see that even at least at degrees of freedom of is equal to 30, we can see the normal the t distribution is becoming a normal distribution within at a higher level degrees of freedom. Beautiful, right? Now this is just a decision because just I want to reiterate it, okay, how you want to think about it. So this is just for your homework or comprehension kind of a thing. I'm leaving this slide for your comprehension much more. Got it? And summing up, okay, if we know the Z statistics, we can simply use the, so if the sigma is known, we use the Z statistics. If sigma is unknown and sample size is small, let's use the t statistics. And of course, sigma is unknown and you have a larger sample size. How do you use it? You can directly use the G statistic. But there is nothing wrong in using t statistics because we are already including the degrees of freedom at that point of time. Okay, because higher the degrees of freedom, the t statistic is becoming a z statistic. So we can just use t statistics ideally for a sample, and if sigma is known, we can always arrive at a g statistics, and there is nothing wrong when we are automating to directly use the t statistics in our automation. Beautiful, right? That's it. And thank you. Let's see in the next episode, which is a very beautiful episode, which will be combining last 3 episodes into one single and I'll be introducing into the hypothesis testing, which is much more crucial and often missed out in most of the data science piece, because everybody these days started focusing on modeling rather than adding business value and testing the business hypothesis or creating new business hypothesis, which I feel in this AI world, going back to those fundamental principles is much more valid rather than following the herd and just doing what everybody is doing. Step back and think, and let's learn the basics. See you soon in the next episode.